So let's continue our discussion of binary trees. And again, so far we are looking at just a generic binary tree with no specific sorting order, but we're looking at traversal. So we saw level order traversal, which is 1, 2, 3, 4, 5, 6, 7 by levels, basically. And usually, of course, again, we go from left to right, but of course, there's nothing saying you can go from right to left. Technically, that also would be a level order, right? Just different one. Very rare to see that, actually. But so pre-order depth first search, right? So basically, again, in this case, traversal 1, 2, right? 4, then 5, then 1, 3, 6, and then 7. All right, so let's look at something called in order, right? This is pre-order. So they are very easy to make, by the way, right? Because once you get this idea, well, once you know how to do one, right, you can do the other ones too. So let's do in order. Let's do in order. So what's changed? Only one thing changes, right? Well, we still need the base case scenario. The only thing changes when do we actually do the visitation. So visit. This is a visit. So-called visit, right? So that's, here we just print it, right? Here it is just printing, but we could do something else, right? That's the only question. When we do the check, when do we check for something, right? Because we're going through the structure. When do we actually check for for some condition or something, right? So that's our visit, basically, right? So the only question now is, of course, what will happen? How will it print? All right, what will it print? Cout. End line, right? Yeah, of course. Why not? On in order traversal will be bt root on end line. Okay, let's see if we can figure this out. So in order, right? So what's the tricky part of it in order? This means that if it's in order, which will be printed first? Which one do you think? In order traversal. In order DFS, right? So,
show the code again?
Okay, show the code. There it is. Very simple. If base nothing, left, traversal right. So think about it. So this means we go left first. We go left as deep left as possible, right? So the first printing will be what number? Which number? 2. Really? We go as left as possible.
Oh, 4.
Yeah, because when you go to left to 2, we don't print 2. We go left. Right, so we go to 4, end up at 4. So this will be 4, right? Let's see what else we're going to have. So 4, then it back up. Again, there's nothing else. So it backs up, right? Because there's nothing left, right? It goes, there's nothing, and then goes right. Then it backs up, prints 2, right? And it should be 4. I think 4, 2, 5, 1. Then, okay, so now let's think about it. 3, is it going to print 3 first? We go right. No, it's going to print 6, I think, first, and then 3, 7. I think this is the hardest one, I think. So let's see if I can do this correctly. 4, we back up to 2, right? Then we check 5, because of course 5 has nothing left, so we do 4, 2, 5. I believe 1. Then we do what? 3 is not going to be printed. 6, 3, 7, I think, right? And again, you don't have to, of course, remember this, right? You just have to get the idea, right? I think we'll see if I did it correctly, right? Maybe I messed up somewhere, because these recursive calls are hard to, do it in your brain, of course, right? So let's run it, and let's see if I made maybe some tiny mistake somewhere. Let's compile. It compiles. It's good. On 4, 2, 5, 1. 4, 2, 5, 1. 6, 3, 7. Okay, very good. So we got it right. On the last one, it'll be easier. By now, you know the drill, right? Finally, we do post order traversal, right? So it's exactly the same. What's the only difference is when we do the visitation, right? Exactly the same, except it's not the same, of course, because it changes when we do the visitation. Again, we visit at the end, right? So if the last thing we ever do is a visit, this after all we visit everything. So it means, okay, we start here, right? So we go left, anything. We go left, right, then we back up 4, right. After we have checked, there's nothing here, so 4 should be printed again, I believe. Let me see if I have this correctly. Okay, let's do one more. Post order. I'll go over here. So post order, DFS. Okay, so I believe 4 should be so 4, and then we back up, right? And then it's gonna be 5. Yeah, it's gonna be 5. So 4, 5, then 2, then again we go down, right, left. Then I think it's gonna be 6, 7, 3, and 1. If I do it correctly, right? So we check we sort of go there. We check the last ones first. The visitation, the priority for the last ones will be checked first, right? So 4, 5, right? Then 2, then 6, 7, 3, and 1. Okay, I think I got it. But let's see if this is the case. I don't know. Maybe I'm wrong. I've been wrong before, right? So let's do this. Post order traversal. Right. All right. Now let's compare. If compilation worked. 4, 5, 4, 5, 2, 6, 7, 3, 1. 6, 7, 3, 1. We got it. All right. So we have all traversals, all basic traversals. Again, we could add, right to left breadth first, I suppose, right? So again, just imagine. So where does this matter? Again, you have these different ways of looking at tree. Remember, these are possible choices. So the visitation is important when we make a decision whether to do something, right? So priority, right? Now again, whether your solution is likely to lie here somewhere, right? Or where somewhere nodes are, where your answer is going to be, right? Maybe you want to check these first, right? Then so if you want to check these first, well, you probably want the post order, probably 4, 5, right, and 6, 7, right? They come first, right? Pre-order, well, you start at the root, right? Again, level order, again, so breadth first, of course, is probably easiest to make, because what's happening here, the issue is, of course, is that these traversals, they were easy to implement, but the downside is we had to use recursion, right? Again, if it's a tree structure, binary tree structure, you're not going to have a problem with the recursive calls too much, because it's a tree structure. You'll depending on depth, right? It's not going to be too many calls. You're not going to reach the limit, right? However, you might still want to know about the possibility of doing this without a recursion. So what does it do? How would you do this without? If you say, okay, I want pre-order traversal, but I don't want to do recursion. Well, what do you do then, right? You say, okay, I'm completely screwed, right? But no, no, it's not. There's always because what's a recursion doing? It's doing its own stack, right? It has a stack of function calls, right? So what you could do is basically you could sort of like make your own. You need some sort of structure to keep of this order, right? We'll see if we can do this. This is usually not taught in the beginning classes, right? Usually not taught at all, but it's possible, right? So we'll see this in a moment. Let's look at the slides a little bit. Maybe there's something interesting in the slides. We know the traversal already. So post order, right? We always look this, right? In order, pre-order, post order, right? So we already saw this, right, in the letters. I checked. So pre-order, right? A, B, D, yes, here C, pre-order, right? Post order, right? F, right? Then D, then B, then G, then E, then C, and A. Yeah, exactly. So also, again, check whether something is empty. It's easy. Check the root. That's easy. So searching for something, again, so this would be the case. If you're searching for something, right, the traversal, depends where it's going to be, right? So we have the height. Okay, how about get height of the tree, right? That might be, I think I might have somewhere question for this, and somewhere it will be some assignment where it'll get the height of the tree, right? Let's determine the height of the tree. Let's make a function. Let's make a function to determine a height of the tree. How? Well, we could of course count it, right? And we could of course add the roots as 0, right? You could sort of like implement it, but let's see. But let's say we don't have it. So get height to be integer, right? We start somewhere, right? Again, possibly we have a subtree. So the trees have this nice property. You take some node, right? You take something here, right? This is also a tree, right? If I do something like this, if I where's my paintbrush? Like if I do something this is also a tree, right? 2, 4, 5. That's also 3, obviously, right? Even this 4 is 3, right? So root you could have subtrees very easy to get. So what do we do? Recursively, if there's nothing, if node is nothing, it's 0. So look at this solution. Return max left right. It's kind of beautiful solution, right? You get a height, right? You get 2 heights, and you return whichever is maximum plus 1, right? So it recursively grows, right? Pretty neat trick, right? Pretty neat trick. So whichever is biggest, right? So it means if you have at least one item, right? So this means, of course, this means here. So this means we have a node, right here. All right. So if you have root, we'll have a height 1, right? Plus 1, right? So let's double check. So what will be the height here? As we know, it should be how much? What's the height here? 2, just 2. If I add 8 here somewhere, right, it will be height 3, right? All right, let's see this. Let's get height. Now height. We'll start at the root, of course. We'll start at the root and we'll see what happens. BT root, right? All right, let's see this in action. Works. And bin 3, height of 3. Okay, 3 actually, right? So we start if this is height 1. So that's a good question actually. Let's look at the literature. Maybe I'm wrong, right? Height of a tree. Let's see what or completely trusty source as the Wikipedia says, right? Base of tree and tip. Yeah. So it is difficult to measure accurately, right? Well, God, this is tree height from a not date structure. This is from actual real tree, right? Yeah, that's not what I meant, of course. Click method, tape method, no. Lidar, I guess, right? No. That's not wrong Wikipedia. Tree height data structure, right? Depth, right? Depth of the tree, right? This is simply. I want official depth and height. Yeah, depth or height. Well, this is 14 years ago, right? Nodes or edges, right? So depth. Let's see this, right? So root node has 0, right? Yeah, so it depends on where you start with, right? So that's one. This is what the guy answered. So root, right? Here height 3, right? Height 0 or depth, right? Depends how you count it, right? Height or depth, right? This guy here is 50,000, but yeah. So 1, 2, 3 here, right? 1, 2, 3. I would say depth, right? Yeah, how deep it goes, right? So height or depth, right? Yeah. So I would say it should be actually 2 here, right? So the question, only thing is how could we implement this, right? If you have nothing, right? So minus 1, right? So height and depth, right? So maybe I should say depth, right? Because this is we going backwards, right? So really, I guess I should call it depth, right? Let's see what our slides say actually. What do they kind? Height. Let's look at this. So we implemented traversal, we did, right? So 3, right? This is slow, right? So this leads, actually we have like 20 minutes. This leads to the second part of this lecture. Is you already touched, and some of you already picked up on this, that of course wouldn't be nice if we actually these binary trees would be actually called binary search trees, right? So what does it mean is we simply add a simple rule. Left side should be smaller, right side should be bigger, right? Everything, right? That's a simple rule. So this is arbitrary. This is not a binary search tree, right? Why? this looks okay. 78, 32 is less, okay, but 60 is not less, so it's broken. So at least, so the thing is, to be a real binary search tree, every possible subtree should follow this rule. That's sometimes people miss it, right? If like it looks like a binary search tree, but there's one small branch which has the wrong rule, it's not a binary search tree anymore because it does not every subtree has this property. So binary search tree, right? This is a binary search tree. Let's see if this is really the case. Let me. Can you see this? Right? This is proper binary search tree, but we have to check. Okay, 50-70 looks good. 50-30, 58 looks good, right? 46 looks good, right? So, by the way, we cannot put 68 here. By the way, either, right? 68 would not be because 60 here, right? 70, 80, 77, right? So the question might be to you: is this the only binary search tree for this data? No. So you probably, I don't know if you learn about this, but the thing is, we'll see that the problem with binary search trees is they can be very unbalanced because the order of insertion matters, right? So how you enter these data points matters. So let's see, we have a binary tree. So how could we make it a binary search tree? Well, we have our nodes. Let's see if we can do it. We have 20 minutes. Only thing is, all it matters is that, well, it has some beautiful properties, binary search tree, because, well, how? What's the advantage of binary search tree? It's like we use our binary search algorithm, right? Yep. We can find things. In what kind of complexity time? If I have a real proper binary search tree, yeah, log n. That again, if it's well balanced, right? I have this log n, and what n is, of course, you have good height, right? Basically, right? It's not, depends on the height of the tree, basically, right? Because we keep dividing, basically. Okay, now, right, so with definition, it's either empty, has a root node, right? Every key in root node is larger than every key in left subtree and smaller than every key in right subtree, right? So it should be true for everything, right? So let's see if we can make a binary search tree, right? This is just a regular binary tree, right? This is a regular binary making a regular binary tree, right? So return max height plus 1. Is there wonder if you could do if I do minus 1, and we'll never get anywhere, right? That's a kind of tricky thing. How could we get the height? It's like this recursive solution. It's kind of tricky to have one less, right? How could we make it one less? You can't do minus 1 because then you have nothing. You'll never have a. You always have 0, 0, 0, 0, 0, 0, 0, 0 plus 1. Well, let's try. I'll try this. Can I do minus 1? No, we have nothing. Because, or return 1. You have nothing. Return 0. I guess. Let's try this. I want to try this one more time. Yeah, okay. Well, we count how many. Yeah, so minus 1 for no h. Okay. Alright. So root, right, will have plus 1, right? So if you have something, right, you'll have 0, right? So root will have height 0. Okay, right? Okay. Alright, so let's do a binary search tree. Binary search tree CPP, or BSTs. They're very famously known as BSTs, right? Let's make a binary search tree. Class, we will also use a structure for a node, right? That holds integers in data and 2 pointers left, right. Okay, let's do it. Include IOStream. A vector. I don't think we use vector actually in this one. Stack Q. This is just everything under the sun, right? But okay. So missing block is node, right? We already have this, right? We could of course include it from somewhere, right? That's our basic block, and now we want, of course, binary search tree class, right? So, class, right? BST, famously known, right? BST, right? Yeah, all right. We'll need a root. Come on, I want some data. I'm too lazy to type this all out, right? I could just copy. So, okay, so BST, node root, and of course our constructor, right? Or constructor, right? We start with nothing, right? Right, so we will insert, right? Typically insert. So how do we insert things, right? So, well, this is wrong. I believe this looks completely wrong. No, this looks completely wrong. We can search for things, right? With BFS, but this is incorrect. This is completely incorrect, right? Because it copied from my previous code. Remember, so this will use a node in proper position in binary, yeah, search tree, every left child, yeah. Okay, let's do this now. Hopefully now it does insert. So if you have nothing, the base case is easy, right? If root is no pointer, we insert it here. Okay, so let's see if this is a recursive call or not. No, it's not recursive. That's good. That's good, right? Parent temporary, right? This is of course very tricky because we are dealing with pointers. So we say, okay, temporary is root, right? Or parent is null pointer for now, because of course there's no parent for temporary. So while temporary is not null pointer, we move around. So we move around and we check left or right. Right? We keep moving, right? And if there is data, if there's parent less, right? We go left. Else we go to the right, right? And is that gonna be it? So we find the right place, right? So we keep, okay, it's actually relatively extremely easy to do it. Why? Because we don't have to insert, we don't have to look at all the tree. We just need to go through in a binary search tree. I'll show you. Maybe my amazing picture, I'll take a new one. So I have here, did you guys ever do this binary search tree thing? Yeah, you did. Okay, so that's easy. So very easy, but could you do it from scratch? Yeah, easy. Right? I want a fat line. So it's kind of okay. Right. So insert, let's say something like 10. Right. So if I insert 15, where is it gonna go?
To the right.
Yeah, 15. Right. And now, how about 12?
Under 15 to the left.
Yep, okay. Now, how about 14?
15 to the right.
Nope. 14, I said.
15 to the left.
And then, we don't remove 12. That's the thing. We don't do anything in a original binary search tree. We don't do anything. We just insert here. We insert 14.
To the left side of
14. So notice it's still under. It's still because remember we do the rule less than 15. We have to go here. Is it more than 12? Yes, we go 14. So this is a binary search tree without any extra algorithms, any balancing algorithms. We just do this, right? So how about, of course, 5, I'll insert here, right? And how about 8?
5 to the right.
Yep. So now you picked up on this, right? So the order of how we insert in a classical binary search tree matters, right? If you have completely random insertion, we'll have very good performance. The issue is the big problem is what? If you have a nice sequence of data, almost sorted, we'll have a really perverse binary search tree. What we end up with? What are we going to end up with? Anyone?
Straight line.
Yeah, which is basically what? What we
List.
linked list, exactly. Very good, very good. You guys know your stuff, right? So very good. So we're almost done. Let me do implementation. Yeah. So we want to avoid. So in the worst case scenario, it could end up like this, right? This is what we are trying to avoid. 1, 2. Yeah. It could happen if you have the wrong order, right? 3, 4. Right. This is a binary search tree. It just so happens to be completely, I would say, almost useless. It's just basically like a linked list, right? It's technically a binary search tree, and this is nothing here, right? Maybe there's, so, okay. So binary search trees by themselves are not the God's answer to everything, right? So because of the balancing issues, right? So, all right. Now, let's see if this works. We have delete node. Yeah, I'm not going to delete anything right now. This is going to be tough because deletion, well, deletion is going to be tricky now, right? For now. We're going to insert. We have search. Now we want delete node. Okay. Tricky, actually. 3 is empty. Does it check? Pop. Delete deepest. No, this is wrong. This is wrong. We can't delete it. We find it. We find the node. And then and then this is a little bit tricky. We'll see what the slides say, right? Search is easy, right? Right, left. Deletion. How do we delete things? This is tricky. So typically, if I delete 60, well, who is going to take the place of 60?
You compare it again.
Yeah, usually you can. So you compared. Well, again, in this case, in this particular case, it'd be really easy. It'd be if you got rid of 70, right, for 60, right, it would be really easy to replace it with 70. If you have no problem, right, it'd be still legal. But unfortunately, usually it's not done like this. Right? We don't know. I mean, the structure, so it's a little bit tricky, right? So 4 cases: leave. If it's leave, it's really easy because you use a leave and not do nothing. Left, no left empty, no right has no empty. So there's 4 cases. So this is very tricky. So maybe I don't think we'll get to this time. I'll see if I have how much time we have. 10 minutes. So we'll probably not do this right now. Try and see what we have for the next lecture. What we have planned for next lecture? Maybe coding aside. Okay, 1 second. Yeah. All right. So let's check. What do we have planned for next lecture? So I don't. So 4 cases. I think we're going to have a graph structure next time, so which is kind of goes together. Maybe we'll be able to finish this. Yeah, graphs, STL, which we already covered a little bit. So hashing, their structures, right, and self-balancing trees, which of course will be interesting, right? So yeah, we'll get to this in a moment. But I guess we can do deletion right now. Let's do the deletion now, right? So yeah, 4 cases, right? So slides mention this, right? So if you delete the 45, where was 45? Here. That was easy, right? How about delete 30? Where's 30? Where is 30? Ah, here. If you remove 30, right? So 35 takes over. That's easy, right? That's very easy. Delete 45. Where's delete 45? So how about here? Delete 80. Delete 50, right? Let's look at this here. Delete 50. Easy. But where does 48 come from, right? Looks like, how did you get up here? This is correct, right? But, so we need to find basically a candidate, right, from the left side, right? Which is the largest from the left side, basically. That seems like that's the case, right? 48, and then we can leave this 45 here, basically. Very tricky, right? Very tricky, these partial cases, right? When you have both children, both sides are full, right? Very tricky. Now, so again, so the analysis, of course, is again the worst case scenario is linear, We already talked about this. But best case scenario, if you're completely random, you have this log 2n performance, which is what we want, right? The only challenge will be how to do this. How to do this? How to balance trees. Oh yeah, and this actually touches on this in order, right? Non-recursive. How to do this non-recursively, right? Basically, node visit, left subtree, right tree. So you move the pointer, you can do this as pointers, right? Same thing for post order and in order. So let me see if I can do this deletion in code. Let's deal. So we have 4 cases. To properly delete a node from the tree, we have 4 cases. Then just delete. Yeah? Has one child? That's easy, right? On in order successor. So this is kind of, again, in order successor. So we need to do some in order traverse. Okay, let's see if this works. Let's see if this works. Value. If there's no root, we are done. Don't do nothing, right? So null pointer, temporary root, right? We have a queue again. We're going to use a queue, right? And we check, right? We keep checking. Well, there's something, right? But again, I don't like this. This is wrong. This is wrong. It's hallucination. This is not how you delete it. Nope. Delete the node from the tree. Or maybe again, let's see if this. Let's see. I don't see any comparisons. It's doing completely incorrect, right? No. This means I have to write myself, and I don't want to. My head hurts already. So no, that doesn't hurt. My head doesn't hurt, but I just don't want to. So search, right? Yeah, that's good. Search. Okay, that's a good start. How about now? Yeah. Right. Else we find it. We need to find the parent. So now, of course, we'll need to find the. Do we need to find the parent? Yeah, be good. So we need to look at search. So this is not very efficient. Not very efficient. Because we already found it here, right? All right. This looks more like it. Right. Yeah. We find the parent, right? But it says just a finding. Right. Right, we have parent has a, right, key node is not root, right, root is not else not pointer, parent gets null pointer, right, parent left, right, so this looks okay. Also, looks very promising, left or right, we take one of, we replace it, and finally, we have both. This is the hardest case, right, we need to find a successor, we need to do in order successor, right, left, right, and of course this will be, notice this delete node, right? This will work, right? Because it's recursive call, right? But this will work because it's going to be outside, and then we do return, right? Return. I think that's it. I think that's returns. That's fine. I think now we're done. I think we have this key node. Where did this come from? We'll see. Is this it? Yeah, that's it. Okay. Now let's test it. Right. Main. We're going to insert. Okay. 5, 10, 5, 15, 3, 7, 12, 18. Okay, well, too much. Well, let's not go there. That's too much, right? We won't be able to see this. Also, we don't have a printer. All right. Let's insert like 7. So 10, 5, 15, 10. Okay, and then we can delete it. Right? Delete. Okay, and now delete 7. 7. No, let's delete. Now let's delete 15. All right. No, we need also a printer maybe, and then we can stop, right? Let's have what kind of traversal do we want? What kind of traversal do we want to see this auction? Probably BFS. Probably let's do BFS. Now let's see. Let's have a level order traversal. Usually no. Right. BFS. Yeah. Right. We know this, how to do this. Okay. Let's do this. Print it. What? Print. Right. On. Let's see if this works. I don't know. Maybe. This is binary search, so I'll call it binary G++, val, out BST. Oh, it compiled, but I don't know if it's going to work. Alright, so it worked. We removed what? 15, right? So how does this work? So 10 is the root, right? 10 is the root. 5, 15. Right, let's see if we can do this. So maybe I could draw this. So 5, 15, 3, 7. So 5 is the first, the second level, right? So 5 has 2 children, 3 and 7. That's correct. 15 has also 2 children, 12 and 18. Now we removed what? 15, right? We removed 15, so 18 takes its place. That looks okay. How about removing 10? Let's remove 10. Let's remove 10 or root. And let's do that, and then we can finish today. Very good. Oh, come on. Right, so who takes over? 12. The right side, right? The right side takes over, right? And then 5. 5, 18, that looks good. And then 3, 7 looks about right as well. Okay, all right. So if you want to practice this visualization, there's a nice tool for. There should be a visualization for this, right? Here, yeah. This part here. I recommend if you want to refresh your knowledge, right? You can start adding some stuff like so. 10, insert, right? 15, insert, right? Insert 5, right? So now we keep inserting bigger and bigger numbers, right? We'll have this bad performance. 25, right? We'll keep inserting. So you don't want this, right? So we'll need to think of, again, in a few lectures, how to avoid this situation, because you keep adding 30 and so on, and you end up with a big linked list, right? All right. So if I add like 2, it's good. Okay, and how about 8? All right. So now let's see deletion. Let's delete 10. So if I remember correctly, 8 should take over, right? There are other possibilities. If I get rid of 10, 8 will move up, right? Let's see if that happens, right? I'll remove 10, right? Is that going to be the case? What else could be take over? Well, 15 could also take over, by the way, here, right? In this particular case, right? Let's see. Maybe 15 will take over, or 8. Either one works in this case. No, 8. Yeah, 8 it is. Yeah. Okay. All right. So again, depending, there are other ways of deleting, but yeah, of course the main thing is you have to keep. So this is not a good binary search tree. Still, it's only, only one choice here, right? The rest are just one way. All right. So thank you, everyone. So Tuesday, right? Reminder about exceptions. We have exceptions homework tonight, right?